August 19, 1943, Rechlin Luftwaffe Test Center, Mecklenburg, Germany. The battered Boeing B-17 Farads sat on the tarmac, its American star barely visible beneath hastily applied German markings. But the bomber itself held little interest for the engineers gathering around the aircraft this morning. Their attention focused on a single device mounted in the plexiglass nose section, a squat, gyroscope-laden mechanism weighing just 50 pounds that would fundamentally challenge every assumption German optical engineers held about precision bombing. The Norden Mark 15 Bombsight, serial number 73428, had survived the bomber's forced landing intact. Over the next 18 months, German engineers would subject this American device to the most comprehensive examination their optical and mechanical expertise could devise. What they discovered would reveal an achievement in precision manufacturing and systems integration that German industry, despite its reputation for engineering excellence, had never approached. The mathematics of strategic bombing were about to be rewritten, not through superior optics or more powerful computers, but through something the Germans had considered impossible: mass-producing a precision instrument to tolerances measured in 10,000ths of an inch, then trusting barely trained bombardiers to use it effectively. The story began 3 weeks earlier over the North Sea. Second Lieutenant Robert M. Hughes of the 94th Bomb Group nursed his crippled B-17 Farads toward neutral Sweden after a disastrous raid on Schweinfurt ball-bearing plants. The aircraft, nicknamed Patches for its battle-scarred fuselage, had taken flak damage that destroyed 2 engines and killed the navigator. Hughes knew reaching England was impossible. Sweden offered the only chance of survival for his remaining crew. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But Swedish airspace proved elusive, as deteriorating weather forced Hughes further east. With fuel exhausted and one remaining engine failing, he ordered the crew to prepare for emergency landing. The B-17 Farads came down hard in a field near Rostock, German territory, on August 2, 1943. The crew survived and entered German captivity. The bomber, remarkably intact despite the rough landing, became prize intelligence material. Luftwaffe recovery teams arrived within hours. They immediately recognized the aircraft's intelligence value and issued orders for careful handling. The bomber was not to be salvaged for parts or destroyed as captured equipment typically was. This B-17 Farads would be transported intact to Rechlin, where technical intelligence specialists could examine everything from engines to ammunition to that mysterious device in the nose that American bombardiers seemed to rely upon so completely. The Norden bombsight had been designed by Carl Norden, a Dutch-American engineer who had worked for Sperry Gyroscope Company before establishing his own firm in 1923. Norden's background in naval fire control systems informed his approach to the bombing problem. He understood that hitting targets from high altitude required solving complex mechanical calculations in real time, while compensating for aircraft motion, wind drift, altitude changes, and ballistic properties of the bombs themselves. His solution combined precision gyroscopes, analog computing mechanisms, and optical systems into an integrated device that could calculate release points with theoretical accuracy measured in feet from altitudes exceeding 20,000 feet. The device entered service with the United States Army Air Forces in 1933, then underwent continuous refinement throughout the 1930s. By 1942, when American bombers began operations against Germany, the Norden represented a decade of development and over $1.5 million in research costs, an astronomical sum for a single instrument. German intelligence had known about the Norden's existence since the late 1930s. Fragmentary reports from American aviation publications mentioned a secret bombsight that enabled unprecedented accuracy. Luftwaffe intelligence analysts dismissed most claims as propaganda. No mechanical device, they reasoned, could achieve the accuracy American sources claimed while withstanding the vibration, temperature extremes, and rough handling of combat operations. German bombsights, principally the Lotfernrohr series developed by Carl Zeiss, used simpler mechanical computers that required bombardiers to manually input data and make continuous adjustments. The devices functioned adequately for level bombing from medium altitudes, but German doctrine had never prioritized the kind of high-altitude precision bombing that American strategic doctrine demanded. The Luftwaffe had been designed for tactical air support of ground forces, not for strategic bombing campaigns against industrial targets deep in enemy territory. This fundamental difference in doctrine meant German engineers had never faced the requirements that drove Norden's design. They had no reason to develop devices capable of what American bombardiers routinely attempted, bombing from 25,000 feet through heavy flak and fighter opposition while maintaining formation integrity and achieving accuracy sufficient to hit specific factory buildings rather than general urban areas. When the captured B-17 arrived at Rechlin in mid-August 1943, Oberst Colonel Edgar Peterson of the Luftwaffe Technical Office assembled a team of specialists to conduct the examination. Peterson, an aeronautical engineer with extensive experience in aviation technology assessment, understood the intelligence value of intact American equipment. He had overseen examinations of captured British aircraft and knew that careful study could reveal capabilities and manufacturing methods that reports and interrogations never conveyed. The team included optical engineers from Carl Zeiss, Germany's premier optical manufacturer. They would examine the Bombsight's optical systems, measuring lens quality and assessing optical design. Mechanical engineers from various armament firms would document the computing mechanisms and gyroscopic systems. Specialists in precision manufacturing would analyze production methods, attempting to determine how Americans achieved the tolerances such a complex device required. The initial examination began with careful photography documenting every external feature before any disassembly. Engineers noted the Bombsight's mounting system, its connection to the aircraft's autopilot, and the control interfaces available to the bombardier. The device sat in a stabilized mount that isolated it from aircraft vibration, while allowing the bombardier to make precise adjustments during the bombing run. What immediately impressed German engineers was the device's apparent robustness. Where German precision instruments typically featured delicate mechanisms requiring careful handling, the Norden seemed designed for rough use. Heavy castings protected internal components. Controls featured positive detents and solid mechanical feedback. The entire assembly could be removed from its mount quickly using simple tools, suggesting American crews performed regular maintenance that German doctrine would assign only to specialized technicians. Disassembly revealed the true sophistication of Norden's design. The computing mechanism used a complex arrangement of gears, cams, and mechanical integrators that continuously solved bombing equations. As the bombardier input data altitude, airspeed, wind conditions, bomb ballistics, the mechanism automatically calculated the correct release point. But unlike German bombsights, that required the bombardier to manually adjust the aircraft's heading to match computed solutions, the Norden connected directly to the autopilot system. During the bombing run, the bombsight actually flew the aircraft, making continuous corrections to maintain the precise heading and speed necessary for accurate delivery. The bombardier's role reduced to tracking the target in the optical sight and inputting corrections for any observed drift. When the mechanism's calculations determined the correct instant, it automatically released the bombs. This level of automation had no equivalent in German bombing technology. The gyroscopic systems particularly impressed German engineers. 3 precision gyroscopes provided stabilization, maintaining the bombsight's reference plane regardless of aircraft motion. The gyros spun at 15,000 revolutions per minute, powered by electrical motors drawing current from the aircraft's generators. German engineers measured the gyroscope bearings and found tolerances held to within 2 ten-thousandths of an inch precision that would challenge even Carl Zeiss's finest instrument makers to achieve in laboratory conditions, yet apparently mass-produced by American factories. Optical engineers examined the sight's telescope, measuring lens quality and optical alignment. The telescope provided 12-power magnification, allowing bombardiers to identify specific target features from high altitude. But what struck German optical specialists was not the magnification German optics could match that, but the lens coatings. Every glass surface bore anti-reflection coatings that reduced light loss and improved contrast. Such coatings remained experimental in German optical manufacturing, applied only to the finest camera lenses and binoculars in small quantities by skilled technicians. The Americans had applied multi-layer coatings to a combat instrument that would be handled roughly, exposed to temperature extremes, and subjected to vibration that would destroy typical optical devices. The coatings appeared durable and uniform, suggesting production methods that went beyond hand-applied laboratory techniques. American optical manufacturing had somehow industrialized processes that German factories still considered specialized craftsmanship. Engineers documented every component, measuring dimensions with precision micrometers and comparing materials analysis conducted on sample pieces. The main casting used aluminum alloy with properties suggesting sophisticated heat treatment and aging processes. Gear teeth showed uniform hardness profiles, indicating precise case hardening procedures applied consistently across multiple components. Even fasteners demonstrated attention to detail. Every screw bore consistent thread forms and head dimensions, suggesting automated manufacturing rather than handmade parts. By late September 1943, the examination team had accumulated enough data to begin preliminary assessments. Peterson convened the specialists to discuss findings. The meeting, documented in reports later captured by Allied forces, revealed German engineers' growing realization that American manufacturing capabilities exceeded previous estimates significantly. Dr. Heinrich Koppenberg, representing Carl Zeiss Optical Works, addressed the precision manufacturing issue directly. The tolerances observed throughout the Norden bombsight required manufacturing equipment and quality control procedures that German factories had never implemented at scale. Individual German instrument makers could achieve comparable precision in laboratory conditions, producing hand-fitted prototypes and specialized devices in small quantities. But mass-producing such precision, building hundreds or thousands of identical units with interchangeable parts, represented a manufacturing achievement Germany had not approached. Koppenberg noted that Carl Zeiss could probably design a device with similar capabilities, given sufficient time and resources. But tooling up production to manufacture such devices in quantity would require years of preparation and manufacturing infrastructure that simply didn't exist in German industry. The Americans had clearly solved production problems that German engineers hadn't recognized needed solving. This realization cut deeply. German engineering pride rested substantially on reputation for precision and quality. Carl Zeiss optics were considered the world's finest. German machine tools set standards for accuracy. German manufacturing emphasized craftsmanship and attention to detail. Yet here sat an American combat instrument, built for mass production and rough field use, that exceeded German laboratory instrument precision while being robust enough to function reliably under conditions that would destroy typical German precision devices. The comparison grew more troubling as engineers examined the bombsight's integration with other aircraft systems. The Norden didn't function in isolation. It formed part of an interconnected system, linking the bombsight to the autopilot to flight controls, and the bombing computer to release mechanisms. American engineers had designed the B-17 with this integration in mind from the beginning, providing electrical power, mounting provisions, and control interfaces specifically suited to the bombsight's requirements. German bombers like the Heinkel He 111 or Junkers Ju-88 had been designed around fundamentally different operational concepts. Their bombsights were auxiliary equipment, not central to the aircraft's design. Retrofitting advanced bombsights into existing German bombers would require extensive modifications affecting electrical systems, control mechanisms, and structural provisions. And even if such modifications proved feasible, German industry lacked capacity to produce advanced bombsights in quantities sufficient to equip bomber units, while simultaneously maintaining production of fighters, which had become the Luftwaffe's overwhelming priority by late 1943. Testing programs began in October 1943 using the captured B-17 Farads as a flying testbed. Luftwaffe pilots and bombardiers trained on the Norden system, learning its operation through captured manuals and experimentation. The goal was to understand not just how the device worked mechanically, but how effective it proved under operational conditions. German test crews conducted practice bombing runs over the Baltic, dropping inert ordnance on target ranges while documenting accuracy. The results confirmed what examination had suggested. In skilled hands, under good conditions, the Norden could achieve remarkable accuracy. German bombardiers who had trained on Luftwaffe sites found the Norden's automation initially disconcerting. Surrendering control of the aircraft to a mechanical device seemed counterintuitive, but after gaining experience, test crews acknowledged the system's effectiveness. What German engineers found most significant was not the Norden's maximum capability under ideal conditions, but its effectiveness under routine conditions when operated by average crews. American training doctrine, revealed through captured manuals and interrogations of prisoners, showed that bombardiers received far less training time than German bomber crews. Yet these less experienced American crews achieved bombing accuracy comparable to or exceeding what veteran German bombardiers accomplished with simpler sights. The Norden's automation compensated for limited crew training by mechanizing calculations and procedures that German doctrine required bombardiers to perform mentally or manually. This represented a fundamentally different approach to solving the accuracy problem. Instead of demanding highly trained specialists who could operate simple equipment expertly, Americans built sophisticated equipment that enabled adequately trained crews to achieve excellent results. The implications extended far beyond bombing accuracy. German military doctrine across all branches emphasized elite training, producing highly skilled specialists. Pilots underwent extensive flight training. Tank crews received months of instruction. Infantry units spent considerable time on combined arms tactics. This approach produced excellent individual units, but it couldn't scale. Training took time, and Germany was running out of both trained personnel and time to train replacements. American doctrine, as revealed through examination of the Norden and other captured equipment, took a different approach. Automate what can be automated. Systematize what can be systematized. Design equipment that works reliably in the hands of adequately trained users rather than requiring experts. This philosophy allowed rapid expansion of American forces without corresponding degradation in effectiveness. A bombardier with 6 months training using a Norden could achieve results that would require years of experience with simpler equipment. By December 1943, German engineers had compiled comprehensive technical reports on the Norden bombsight. These documents, stamped Geheim, secret, and distributed only to senior Luftwaffe technical staff and armaments ministry officials, painted a sobering picture of comparative capabilities. The reports acknowledged American achievements in precision manufacturing, systems integration, and production engineering that Germany had not matched. One report, authored by engineers from the Reich Air Ministry's technical division, stated the conclusion directly. The manufacturing precision observed throughout this device exceeds capabilities currently available in German instrument production. Replication would require extensive retooling and development of manufacturing processes not currently employed in German industry. Time required for such development, minimum 2 to 3 years, assuming availability of adequate resources and personnel. The report continued with even more troubling observations. More significant than the device itself is what its construction reveals about American industrial capacity. The precision and consistency observed across all components indicates mass production using automated processes and precision tooling. Parts appear fully interchangeable, suggesting manufacturing tolerances held consistently across large production runs. Such manufacturing capability represents industrial maturity substantially beyond current German capacity in precision instrument production. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. These assessments reached Albert Speer, Reich Minister of Armaments and War Production, in early 1944. Speer, responsible for German industrial output and keenly aware of resource limitations, understood the broader implications immediately. Germany faced not just a technological gap in specific weapons systems, but a fundamental industrial capacity gap that would only widen as the war continued. American factories could mass-produce precision instruments to tolerances. German factories achieved only in small-scale production. American manufacturing systematized processes that German industry still treated as specialized craftsmanship. American design philosophy prioritized reliability and ease of production over theoretical performance optimization, resulting in weapons that worked consistently in field conditions rather than achieving impressive specifications that couldn't be maintained in combat. Speer had already confronted similar revelations about American manufacturing capability through examination of captured Sherman tanks, B-17 bombers, and other equipment. Each examination revealed the same pattern. American engineering emphasized practical functionality and mass production over German preferences for theoretical perfection and craftsmanship. The Norden bombsight simply provided additional confirmation of what was becoming undeniable. American industrial capacity exceeded German capabilities by margins that couldn't be overcome through superior tactics or technological innovation. Additional captured Norden bombsights reached German hands through 1944 as more American bombers went down over occupied Europe. Each captured unit underwent examination, building a comprehensive database of production variations and manufacturing techniques. Engineers noted that bombsights captured from different production periods showed evolutionary improvements later. Units incorporated refined components and simplified assembly procedures while maintaining or improving performance. This continuous improvement in production, accomplished while maintaining high output rates, demonstrated manufacturing sophistication that impressed German engineers familiar with their own industry's struggles. German weapons production frequently encountered quality degradation as output increased. Expanding production meant employing less skilled workers, using lower quality materials as shortages worsened, and accepting tolerances that would have been rejected earlier in the war. American production showed the opposite trend. Quality improved as production increased, suggesting that Americans treated manufacturing as an engineering problem to be systematically solved rather than a craft to be performed by skilled workers. They designed production processes that built quality into the system rather than relying on worker skill to achieve quality outcomes. The Carl Zeiss Optical Works assigned responsibility for potential German bombsight development based on Norden principles, conducted detailed feasibility studies through spring of 1944. Engineers calculated tooling requirements, manufacturing timeframes, and resource needs for producing in German, equivalent to the Norden. The conclusions, delivered to the Reich Air Ministry in May 1944, effectively ended any consideration of copying or matching American bombsight technology. Zeiss engineers estimated that developing production capability for Norden-equivalent bombsights would require minimum 36 months from initiation to first production units. Tooling costs would exceed 8 million Reichsmarks. Production would require materials including high-grade aluminum alloys, precision ball bearings, and optical glass, all materials that were already in critically short supply for existing weapons programs. Manufacturing would demand skilled workers and precision machine tools that were desperately needed for fighter production, which had become Germany's absolute priority as Allied bombing intensified. Even if all resources were made available immediately, the Zeiss report concluded, German industry could not produce bombsights in quantities sufficient to equip even a fraction of remaining bomber units before 1947 at earliest. By that date, the war would be long decided. The report recommended abandoning any attempt to match American bombsight technology and instead focusing limited resources on defensive systems, radar, fighters, and anti-aircraft artillery that might disrupt American bombing effectiveness regardless of bombsight capabilities. This recommendation reflected strategic reality that German military leadership increasingly confronted through 1944. Germany could no longer compete with Allied industrial output across multiple weapons categories simultaneously. Choices had to be made. Resources allocated to one program meant resources unavailable for others, and with Allied strategic bombing systematically destroying German industrial capacity, those resources were shrinking steadily. The Norden bombsight had become tactically less relevant to Germany's situation by mid-1944, for another reason. American bombing tactics had evolved in ways that reduced reliance on precision bombing from high altitude. The 8th Air Force, facing devastating losses during deep penetration raids in 1943, had adopted formation bombing tactics where lead bombardiers aimed for entire bomber streams. When the lead bombardier released bombs, all following aircraft released simultaneously, creating a pattern of explosions that saturated target areas rather than achieving pinpoint accuracy. This tactic, born of necessity after losses forced changes in doctrine, actually reduced demands on individual bombsight accuracy. The Norden's theoretical capability to place bombs within feet of an aim point from high altitude became less critical when missions dropped thousands of bombs across target complexes measured in acres. Formation bombing emphasized overwhelming destructive power delivered to general target areas rather than surgical strikes on specific buildings. German air defenses, particularly flak concentrations around vital targets, had forced American bombers higher often to altitudes exceeding 28,000 feet, where even the Norden's accuracy degraded significantly. Defensive requirements drove tactical evolution that partially negated the technological advantages the Norden provided. Yet, even reduced to formation bombing from extreme altitude, American strategic bombing achieved devastating effects that German defenses could not prevent. Testing of the captured Norden continued at Rechlin through 1944, but the focus shifted from understanding the device for potential replication to understanding it for defensive purposes. If German fighters could disrupt American formations during bombing runs, accuracy would degrade regardless of bombsight capability. If flak could force bombers to take evasive action, the Norden's automation became liability rather than advantage. The device required straight, level flight for its calculations to remain valid. German fighter tactics evolved to exploit this vulnerability. Luftwaffe pilots learned that aggressive attacks during the final bombing run, when American formations had to maintain steady courses for bombsight operation, could disrupt aim and scatter bomb patterns, even if the attacks didn't destroy bombers. Flak batteries learned to create barrage patterns that forced evasive maneuvers, accepting that most shells would miss in exchange for disrupting bombing accuracy. These defensive adaptations helped German defenders survive longer than pure attrition mathematics suggested possible. But they represented reactive measures, responses to American capabilities rather than proactive strategies. Germany had lost the initiative in strategic air warfare and could only react to American actions, never seizing control of the campaign's direction. By autumn of 1944, examination of the Norden bombsight had revealed everything German engineers could learn from the device. Final reports acknowledged American superiority in precision manufacturing, systems integration, and production engineering. They documented specific technical achievements: gyroscope, precision, optical quality, mechanical computing sophistication that exceeded German capabilities. They explained how American design philosophy differed from German approaches, emphasizing automation, interchangeable parts, and ease of production. But the reports also revealed what examination alone couldn't teach: how to replicate American manufacturing systems. Understanding that Americans achieved precision through automated processes and precision tooling didn't provide the tools, the trained workers, the organizational systems, or the time necessary to implement similar approaches in German industry. Knowledge without capacity to implement that knowledge provided little practical benefit. The captured B-17 Farads used for Norden testing met its end in March 1945 during an American bombing raid on Rechlin. The aircraft, still bearing German markings, was destroyed on the ground along with much of the testing facility's infrastructure. The Norden bomb site itself survived and was evacuated westward as Soviet forces advanced. It eventually fell into American hands after Germany's surrender in May 1945. Post-war interrogations of German engineers who had examined the Norden revealed their conclusions about American manufacturing superiority. Dr. Koppenberg from Carl Zeiss, questioned by American technical intelligence officers, acknowledged that German optical manufacturing had never achieved the production sophistication the Norden demonstrated. Individual German craftsmen could produce comparable precision in laboratory conditions, he explained, but industrializing such precision, building it into automated production systems, represented capabilities German industry had never developed. Other engineers made similar admissions. The precision wasn't theoretical impossibility. German engineers understood the physics and mathematics involved. The challenge was manufacturing at scale, American factories could produce thousands of units to tolerances that German factories achieved only through hand-fitting and individual attention. This represented not superior scientific knowledge, but superior industrial organization and manufacturing methodology. The implications extended beyond bomb sites to fundamental questions about industrial capacity and its role in modern warfare. Germany had entered World War II with technological advantages in many weapons systems and superior tactical doctrine across multiple domains. But Germany lacked the industrial depth to sustain those advantages through years of attrition warfare against opponents with vastly greater manufacturing capacity. The United States entered the war with weapons that were often less technologically sophisticated than German equivalents. American tanks had weaker guns and thinner armor than German heavy tanks. American fighter planes initially had lower performance than German fighters. American artillery used older designs than German guns. But American industry could produce these weapons in quantities that overwhelmed German forces, regardless of individual unit superiority. More importantly, American weapons were designed for mass production and field maintainability. They incorporated interchangeable parts, simplified maintenance procedures, and generous design margins that allowed rough handling and minimal training. These characteristics, which German engineers sometimes dismissed as crude or unsophisticated, proved far more valuable in sustained combat than theoretical performance advantages that couldn't be maintained under field conditions. The Norden bombsight exemplified this American design philosophy perfectly. It automated complex calculations that German doctrine expected bombardiers to perform manually. It connected to aircraft systems in ways that German bombs had never integrated. It used precision manufacturing to ensure reliability, rather than demanding expert maintenance to preserve functionality, and it could be produced in quantities sufficient to equip thousands of bombers, not just elite units. German examination of the Norden had revealed all these facts by early 1944. Reports documented the findings with scientific rigor. Engineers reached correct conclusions about American capabilities and German limitations. But understanding a problem and solving it are different challenges. Germany lacked the time, resources, and industrial capacity to reorganize manufacturing along American lines, while simultaneously fighting losing battles on multiple fronts against enemies with overwhelming material superiority. The story of German engineers examining the captured Norden bombsight represents one of many instances where German technical intelligence correctly identified Allied advantages but could do nothing effective with that knowledge. Similar patterns emerged from examination of American radar systems, proximity fuses, and cryptographic equipment. In each case, German engineers understood the technology, recognized American manufacturing superiority, and concluded that Germany could not match Allied capabilities within timeframes relevant to the war's outcome. Post-war analysis by American intelligence organizations confirmed what German examination of the Norden had revealed from the opposite perspective. The United States Strategic Bombing Survey, which conducted comprehensive studies of bombing effectiveness, concluded that the Norden bombsight had contributed significantly to American strategic bombing success. But the survey also noted that the bombsight's value came not from enabling pinpoint accuracy, which proved impossible to achieve consistently under combat conditions, but from providing adequate accuracy reliably across thousands of missions by crews with limited training. The Norden's automation meant that average crews could achieve results that would have required expert crews using simpler equipment. This democratization of capability through automation represented a fundamental American advantage across many weapons systems. While German doctrine emphasized elite units equipped with sophisticated weapons requiring expert operators, American doctrine emphasized adequate equipment that functioned reliably in the hands of adequately trained users deployed in overwhelming numbers. The mathematical logic proved undeniable. 10 bombers with Norden bombsights hitting targets with 70% effectiveness delivered more destructive power than 3 bombers with superior manual bombsights hitting targets with 90% effectiveness. And American industry could produce the 10 bombers while training their crews faster than German industry could produce 3 bombers while training elite crews to expert proficiency. In the decades following World War II, The lessons German engineers learned from examining the Norden influenced European manufacturing development significantly. Engineers who had documented American production methods during wartime applied those lessons to post-war reconstruction. They understood that matching American industrial output required not just copying American products, but implementing American production philosophies, automation, standardization, interchangeable parts, and systematic quality control. The transformation took decades, but eventually succeeded. By the 1970s, European manufacturers had closed the production efficiency gap that had been so apparent during World War II. German optics firms like Carl Zeiss implemented automated production methods that achieved precision at scale comparable to American manufacturers. European aerospace companies developed production systems that combined traditional European craftsmanship with American mass production efficiency. The captured Norden bombsight, that 50-pound device removed from a damaged B-17 Farads in August 1943, and had taught German engineers that their defeat was inevitable, not because of inferior scientific knowledge or engineering expertise, but because of inferior industrial organization and manufacturing capacity. More importantly, it taught them why American manufacturing succeeded where German production failed, through systematic application of automation, standardization, and production engineering principles that treated manufacturing as a solvable engineering problem rather than an art requiring skilled craftsmen. Those lessons, learned through careful examination of an enemy's equipment, became the foundation for Europe's post-war industrial development. The engineers who had measured gyroscope tolerances and documented optical coatings in 1943 and 1944 became architects of European manufacturing modernization. They had learned by examining aluminum and glass and steel that modern industry belonged not to those with the most skilled individual craftsmen, but to those with the most effective production systems. The Norden bombsight dropped its last bombs in 1945, becoming obsolete almost immediately as radar bombing and guided weapons rendered mechanical computing bombsights unnecessary. But its influence on manufacturing philosophy and industrial organization extended far beyond its tactical combat use. In engineering schools today, the story serves as a case study in how examination of competitors' products can reveal invisible systems and methodologies that matter more than visible technical specifications. It demonstrates that understanding an opponent's methods matters more than copying their designs. It shows that the principles of production ultimately determine the outcomes of industrial competitions, whether in warfare or commercial markets. The Boeing B-17 flying fortresses, carrying Norden bombsights, dropped 640,000 tons of bombs during World War II, contributing significantly to Germany's defeat through systematic destruction of industrial capacity. But perhaps the Norden's most important contribution was the lesson it taught when German engineers examined captured examples with scientific rigor and documented their findings with characteristic German thoroughness. Those engineers discovered that American industrial power came not from superior materials, better designs, or more advanced scientific knowledge. It came from superior organization of the manufacturing process, from systematic application of automation, precision tooling, interchangeable parts production, and quality control methods that enabled less skilled workers to produce precisely manufactured products rapidly and consistently. The captured Norden bombsights examined at Rechlin are long gone, destroyed more than 70 years ago in the war's final months. But the lessons they taught transformed manufacturing worldwide and influenced industrial development for generations. Engineers and manufacturers globally learned that precision and mass production were not opposites but complementary aspects of properly organized industrial systems, that automation could extend capability rather than replace skill, and that production methodology mattered as much as product design in determining competitive success. The story that began in August 1943, when German engineers first examined that battered bombsight removed from a captured B-17 Farads, ended decades later with fundamental transformation of global manufacturing. The examination had taught German engineers that their wartime defeat was inevitable given the industrial capacity gap. More importantly, it taught them why, and in understanding why, they learned how to ensure that industrial inadequacy would never again limit European capabilities. The Norden bombsight served as teacher to its enemies, and they learned the lesson well, perhaps too well, as post-war European and Asian manufacturers eventually challenged American industrial dominance using principles that American engineers had demonstrated during World War II. The captured device revealed not just technical secrets but philosophical truths about the nature of modern industrial competition. Those truths remained valid long after the specific technology became obsolete, continuing to shape manufacturing strategy and industrial organization into the 21st century. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.